We now need to turn our sights on to exponential and logarithmic functions. So you've studied exponential and logarithmic functions in pre-calculus. So just a quick review of some of the things that you saw in pre-calc with these two types of functions. One, you should understand that they are the inverse of one another. The exponential function graphically looks like this. It has a horizontal asymptote down on this end. It's an increasing function. It's concave up. The logarithmic function looks like this. And when I say exponential and logarithm, I'm talking about natural exponential and natural logarithm, where both of them are base e. And so this function, has this shape to it. It's an increasing function as well, but this one's concave down. Since they're the inverse of one another, they're symmetric with respect to this identity line, y equals x. And we understand the idea that if y equals e to the x, then x equals log y. That's the concept of two functions being the inverse of one another. Other things you should understand about these functions is what their domain and ranges are. What can you plug into the function, what kind of answers come out, and you can kind of see that really largely from the graph. So with the natural exponential function, you see that this function is completely above the x-axis. So as far as its range go, the range is simply only positive values from 0 to infinity. However, the x values that we can use for this function, since it ranges from the far left all the way to the far right, is really all real numbers. So its domain is all real numbers, but its range is only positive values. You see from the graph that the function is continuous, it's increasing, it's a one-to-one function, which basically tells you that it's going to have an inverse. We also see that it's concave up, the way that it's curving up. And a couple of things to understand is that the limit as x goes to infinity, negative infinity, this one right here should be negative infinity for this one right here, is going to be 0, but the limit as x goes to positive infinity would be infinity, because on this end we have a horizontal asymptote, and on this end we're going up to positive infinity. A lot of the same stuff can be seen with the logarithmic function. Also, one thing you should understand is that since two functions are the inverse of one another, the domain and range flip for the log and the exponential, if you look at that. So in the logarithmic function that looks like this natural logarithm, the domain is now only positive values and the range is all real numbers. And you see that from the graph. The graph only sits on this side of the x-axis, which means you're only going to use these x values, so the positive x values. But the y values that you're working with go from negative infinity all the way up to positive infinity. This thing doesn't increase very quickly, but it does keep increasing the whole way. So it's a continuous function, it's an increasing function, it's a one-to-one function. It's concave down, in this case it's curving down as opposed to the exponential, which was curving up. And a couple of things to look at in terms of limits is as I approach 0 from the right hand side, and so as x goes to 0 from the right hand side here, you see that this function is turning down, in which case the y value is going to negative infinity. But as x goes to positive infinity on this end, the function continues to rise because it's increasing, and the function will eventually go to infinity. So recall that we had some properties of logarithms back in pre-calc. A couple of them. One is just based off the definition of a logarithm that the log of 1 equals 0. The other three are these expansion properties, that if you have a product inside a logarithm, you can turn it into the sum of two logs. If you have a power inside the logarithm, you can pull it out as a constant multiple. This is really just a version of this one. And the quotient inside a logarithm you could turn into subtraction of log. So this would be basic properties you would have learned again in pre-calc. We call those the expansion properties. So what it allows us to do is to take something like this logarithm here and write it as multiple logarithms added, subtracted together. And so if you look at this whole thing is inside your logarithm. This is a multiplication, this is multiplication. So I could write this as the natural log of 5 plus the natural log of x cubed plus the natural log of the square root of 3x plus 2. Now I can go a little bit further here because this natural log of 5 I can't really do anything with, but this is a power inside which I could pull out to the front of this logarithm, and the square root can be written as a 1/2 power. So I can write this as 1/2 natural log of 3x plus 2. And so this is really the same thing as this original one, but it's multiple logs added together instead of one single log. This is going to be really helpful when it comes to doing derivatives. We can do the same thing here with this one. In this case, we have some division, so we can use subtraction. So we write this as the log of x squared plus 3 squared minus the log of x times the cube root of x squared plus 1. Then we can pull the power out. X squared plus 3 minus, this one's going to turn into a product. Now, if this is going to expand from a product into addition and it's being subtracted, that whole thing is going to need to be subtracted still. So write this as the log of x plus the log of, I'll write this as x squared plus 1 to the 1/3 power. It's a cube root, so I'll write it as 1/3 power. But notice subtraction outside the whole thing. Because while this expanded, this logarithm was being subtracted. All right, so then the last step would be this power here can come out to the front of this single logarithm. I could distribute that negative into here now, so I could write this as 2 log x squared plus 3 minus log x minus 1/3 log of x squared plus 1. Another thing you got to remember from pre-calculus when you learn about these functions is the inverse property. And the inverse property says that if we take the composition of two functions that are the inverse of one another, what happens is essentially they cancel each other out and give you x. So if I took the log of e to the x, I would just get x. Or if I took e to the natural log of x, I would get x. So we're not going to use this a ton for what we're going to do, but it's something you should remember. Essentially what we think of is like the log and the e almost cancel each other out and you're just left with the x in both cases. Now it's not canceling, it's a property of composition and inverses, but it's kind of the way we can think about it. And so we use that a lot to solve equations like this. You know, we want to figure out what x equals. And in order to figure out what x equals, the problem is x is up in the exponent. And so I'll take the natural log of both sides of this equation. And what that allows me to do essentially is, since these are the inverses, they would cancel each other and give me natural log of 7 equals x plus 1. I could then subtract the 1 over to the other side, and I would get the natural log of 7 minus 1 equals x. And so that's the solution for x. Okay. Again, we're not going to do a ton of this, but these are all different things that you would have learned when you first started talking about logarithms and exponentials. What we really want to talk about is how we take the derivatives of these natural exponential and natural logarithmic functions. The definition for why the derivative is what it is, we can go back to that original limit definition that we talked about with derivatives. I think at this point it's best to just learn what the derivatives are and then start using them. In this case, we start with the exponential function. It's fairly easy to come up with the derivative of the exponential function. In this case, the derivative of e to the x is e to the x. I mean, it can't get too much easier than that. Now, you're only going to do that so many times. If you look at these examples I have down here, it's not e to the x, it's e to the 5x plus 3, or e to the negative 3x over x, or x cubed times e to the x squared. And so none of those are just e to the x. So what we're going to do mainly is use this version of the derivative rule, which is the chain rule version of this derivative rule. And so you think about this as outside function and inside function. So this e to the power, e to the power is the outside function, and the power itself is the inside function. So when we do the chain rule, what do? We take the derivative of the outside function. Well, derivative of e to something is e to that something. So that's how we write this here. So e to the u. But then since u isn't just an x, u is a function of x, we then have to multiply by the derivative of that inside, u being the inside, and that's du dx. You could also write this as e to the u times u prime. So whatever you feel more comfortable with. So in looking at these examples, if I was going to do this derivative here, I would rewrite the exponential, then multiply by the derivative of the exponent. In this case, that's 5. So I'll write this as 5e to the 5x plus 3. Go to the next one. If I was going to do this, I would say, okay, rewrite the exponential, e to the negative 3 plus x over x times, then I have to take the derivative of that exponent, 3 plus x over x. Now, how am I going to take the derivative of that? Well, I could sit here and use I could use the quotient rule. So, e to the negative 3 plus x over x times, if I do the quotient rule, derivative of the numerator would be 1 times the denominator minus, derivative of the denominator would be 1 times the numerator, all over the denominator squared. Simplify that, and you end up with e to the negative 3 plus x over x times, distribute this negative in here, what you see is you have an x, and this negative going all the way to here gives you a minus x. This minus and minus gives you a plus 3 over x squared. I could leave my answer like that. I could write it as 3e to the negative 3 plus x over x all over x squared. That doesn't really particularly matter, but that's how you would do that derivative. Now on this last one, before we start thinking about taking the derivative of the e, the natural exponential, what we really have here is a product. And so to start taking the derivative of this one, we're going to need a product rule. And so we take the derivative of the x cubed, which is 3x squared. The e to the x squared stays the same, plus x cubed times the derivative of e to the x squared. Well, that's now we're going to take the derivative of this exponential. So what do? We rewrite the exponential, then we multiply by the derivative of the exponent. Simplify a little bit, since these are all multiplied together, I'd take these two and multiply them. So I have 3x squared e to the x squared plus 2x to the fourth e to the x squared. I could factor stuff out of here, but that doesn't really simplify it any. It just rewrites it in a different way. So ultimately there is your derivative. So you see, taking the derivative of these natural exponentials is pretty basic. I mean, there's not really a ton to it. The hardest thing you would have to do is really think about using the chain rule here, where you have to multiply by the derivative of the exponent, because that's the inside of the function. So now we need to talk about taking the derivative of a natural logarithm. And so we need to spend a little bit more time with this. There's more that we can do with this. It's a little more involved. First, just let's look at the derivative of the natural logarithm. We can talk about where this came from. In one way, we can talk about the fact that this is the derivative, this is the inverse of the exponential. And if we know the derivative of the exponential, we can find the derivative of the logarithm. We also could just come up with the derivative of the logarithm on our own using the limit definition. Lots of different ways to do this. Right now, we're just going to learn what the derivative is. And so if we're looking at the natural log, and we want to take the derivative of the natural log, the derivative is 1 over x. Notice it says for x greater than 0. That's because, remember, with a log, you can only take the log of a positive value. You can't take the log of 0. You can't take the log of a negative. So we have this value of x greater than 0. And we'll talk about that. We can change that a little bit later, depending on how we look at this logarithm. We'll get to that. But how many times are you going to take the log of just x itself? Look at these examples. Log of 5x, log of 5x squared plus 2. This is log of x squared. And so this derivative rule has to be expanded a little bit. And we can use the chain rule to expand it. So let's say we had the log of u, where u is a function of x. Okay? In which case we're going to use the chain rule, the derivative of the outside function, which would be the log of something, which the derivative log of something would be 1 over that something, so log of u is 1 over u. Then we have to multiply by the derivative of the inside, and the inside is your u, so du dx is the derivative we multiply by. We could also write this as u prime over u. If you think about that, that's 1 over u times du dx, which is u prime. Well, 1 over u times u prime is u prime over u. So, that's where that comes from. I think this is the easiest one to work with. U prime over u is the easiest one to remember as well. So when you're taking the derivative of log of u, the derivative rule that we're going to go by and we're going to have to memorize is u prime over u. So looking at this first one, the derivative of log 5x, 5x being my u. And so the derivative of 5x is 5 over 5x itself. This is u prime over u, where the 5x is my u. Cancel out the 5's, and you see you get 1 over x. Pretty simple derivative. Go to the next one. If I'm going to do the derivative of log of 5x squared plus 2, well, that's my u right there, 5x squared plus 2. So the derivative of 5x squared plus 2 is 10x divided by the 5x squared plus 2. Again, that's u prime over u. Again, pretty easy derivative. As far as canceling goes, there's no canceling going on here. Don't try and cancel this 5 and this 10. That's not going to happen. The 5 is got connected to the x squared with the plus 2. No canceling going on there, not a common factor. All right, looking at this next one, there's a log involved, but there's also a product here, x squared times the logarithm. So in order to do this derivative, we have to use the product rule. So I'm going to take the derivative of the x squared times the log plus the x squared times the derivative of the log, which is 1 over x. I can simplify this piece a little bit. So I have 2x log x, cancel an x out of that. We're left with just x. And so there's my derivative. This next one, there's a log, but there's a little bit more going on here. So we have quite a bit of compositions going on. We have an outside function and we have an inside function. So first, that's a chain rule problem. So 4 now to the third, the inside stays the same. We then multiply by the derivative of the inside. Now, if we're going to take the derivative of this inside, now that's a logarithm. We're going to use the u prime over u rule to get that done. Simplify that a little bit. We have 4 log x squared cubed. The x's will cancel out of this, so I have 2 over x. I can multiply this 2 with the 4, so I got 8 log x squared cubed all over x. So when looking at this one, this was a chain rule to start, but the log itself is a chain rule, so it's a chain rule inside of a chain rule problem. Here we need to differentiate another logarithm. This one's a little more difficult. I mean, in this case, this piece right here, this square root of 5x squared plus 2 is your u. So if we use the fact that the derivative of this logarithm should be u prime over u, we would have to take the derivative of the square root of 5x squared plus 2 and then divide by the square root of 5x squared plus 2. That's not too difficult, but it also doesn't look too great either. To take this derivative here, we would need to use the chain rule, but there's an easier way. So remember the log properties, that if you have a power inside a logarithm, it can come out as a multiple addition, multiplication inside a log can turn into addition, division can turn into subtraction. What I can do here is I can rewrite this function as log of 5x squared plus 2 to the 1/2, which I could then write it as 1/2 log of 5x squared plus 2. It's still just the original function. I haven't taken the derivative yet. So now if I go to take the derivative, the 1/2 is a constant multiple, and now I'm taking the derivative of this. Now I'm still going to use the u prime over u, and here's my u, but now that is easier to take the derivative of than that was. So I take the derivative of 5x squared, I'm going to get 10x over 5x squared plus 2. That's the u prime over u. And there's my derivative. Now I'd simplify this a little bit. This 2 here can cancel with the 2 that's in the 10 and leave me with a 5. So I have 5x over 5x squared plus 2. Don't cancel these two 5's because you can't. This 5 is not a factor. But nonetheless, there's your derivative. A little bit easier. So sometimes if you look to use your log properties, you can make these derivatives easier on yourself. This one is a prime example. I mean, if we had to use the u prime over u rule to take the derivative of this logarithm, this whole thing right here is my u. So I'd have to take the derivative of this and then divide by this whole thing. You could see that would be pretty messy. However, if I use my log properties first and take my function and rewrite it a different way. So first, log of x times 2 minus x squared cubed minus log of 5x to the fourth minus 3 to the 1/2. Take the division and turn it into subtraction. Then this multiplication here can turn into addition. So I have log x plus log of 2 minus x squared cubed minus log of 5x to the fourth minus 3 to the 1/2. Then this power can come out to the front and this 1/2 can come out to the front. So I have log x plus 3 log of 2 minus x squared minus 1/2 log of 5x to the fourth minus 3. Now that's still just the original function. That's not the derivative. But this version of the original function is much easier to differentiate. So now if I look to take the derivative of the function, since they're added and subtracted from one another, I can do each one separately. Well, derivative of this log is 1 over x, plus 3 times this log's derivative would be minus 2x over 2 minus x squared, minus 1/2 times the derivative of this log would be 20x cubed over 5x to the fourth minus 3. Right? If we can simplify, we would, and then we're done. So this 1 over x, not much there. This 3 can be multiplied in, so I get minus 6x over 2 minus x squared. This 2 and this 20 can cancel, give me a 10, so I have minus 10x cubed over 5x to the fourth minus 3. So there's your derivative. If you wanted to write it a different way, we could put this all together as one fraction. The common denominator would be x times 2 minus x squared times 5x to the fourth minus 3. You would multiply each fraction by something and do that computation. That's not necessary. This is fine for right now. But if you had to write it a different way, that would be the only way you'd do it. Okay, so now we have this question. Y equals x minus 3 squared over the square root of x cubed plus 2. You want to take the derivative of this thing. So in taking the derivative of this, think for a second. Well, how would I do this? This one, if you notice, doesn't have a log on it. So what we just did on the last question really doesn't apply here. So this is a quotient. So if this is a quotient, I would have to use the quotient rule. In the quotient rule, I'd be taking the derivative of the numerator and the denominator. Each one would require the chain rule. And so you could see this could be kind of messy, but should be doable based off of what we've learned so far this semester. However, there's another way. If this did have a log out in front of it, this would look a lot like the last one. In which case we could start breaking this division apart with subtraction. These powers can come out, etc. But it doesn't have a log there. So question is, how do we get this to work? Can we just throw a log into this if we feel like it? And the answer is actually yes. What you're going to use is basically your general rule for equations. Whatever you do to one side of the equation, you got to make sure you do the same thing to the other side. And really, this is an equation. Y equals x minus 3 squared over the square root of x cubed plus 2. And so being an equation, I can take the log of both sides of this equation. Now that's going to have some consequence as we go through, but it's definitely legitimate for us to do. Why do we want to take the log of both sides? Because on the right hand side, now I can take this and break this apart into 2 log of x minus 3 minus 1/2 log of x cubed plus 2. And that's still just log y on the left hand side. Notice we haven't taken the derivative yet. And ultimately, what are we trying to find? If you're trying to find the derivative of this, you're trying to figure out what y prime equals, right? So now comes time to take the derivative. So we took the log of both sides, we applied our log properties. Now if we take the derivative, we have to do that on both sides of this equation, just like we had to take the log on both sides. So if I take the derivative of this side here, well, if the derivative of log of u, if that derivative is u prime over u, then the log of y should be y prime over y. and keep going. This will be 2 times 1 over x minus 3 minus 1/2 times 3x squared over x cubed plus 2. Simplify if you can. But ultimately what we right now have is what y prime over y equals. Remember, we're trying to figure out what y prime equals. Well, that's not bad. We could take this y and move it to the other side. So we have is y prime equals y times 2 over x minus 3 minus 3x squared over 2 times x cubed plus 2. And we could say that that's what the derivative is, but we could do a little bit better too. I mean, think about it, if we did the quotient rule all the way up here, we didn't do this stuff with logarithms, we wouldn't have an answer that had y's and x's in it. So the fact that we got that here is probably not that great. So what we'll do is we'll try and go all to x. Well, we can do that because this is y, and we know what y equals. Y equals this right here. So we'll rewrite that as x minus 3 squared over the square root of x cubed plus 2 times this whole thing. But I'm going to put that together as one fraction. So it'll be x minus 3 times 2 times x cubed plus 2 as the common denominator. The 2 should be multiplied by this denominator. So that'll be 2 times x cubed plus 2. Then minus the 3x squared should be multiplied by this one, which will be x minus 3. Okay, and I did that for a reason. That's what y prime equals. The reason why I did that was this. If you look, we have some common factors that can cancel here. This x minus 3 and this x minus 3 are common factors. This is to the second, this one's to the first. This x cubed plus 2 is really to the 1/2 power. This x cubed plus 2 is to the first power. We can put those together. So we could do some simplifying by putting this thing as a single fraction. So what are we going to get? Let's bring this up here. Our y prime equals, if I cancel this x minus 3 with one of these, I'll have x minus 3. If I take these two and put them together, well, this one's to the 1/2 power technically, and this one's to the first, and they're being multiplied together. Then what I should do is I should add the exponents. So in the denominator, I'll have x cubed plus 2 to the 3/2 power. This 2 is still here. This is a 3. This 2 is still here. Okay. Then I just have to do this computation. So this is 2 times 2, which is 4 distributed into there. So that'll give me 4x cubed plus 8. Then this will distribute into here, which will give me a minus 3x cubed plus 9x squared. So ultimately what that gives me is x cubed plus 9x squared plus 8. And so there's your derivative. That's the simplest version of it. We can't simplify anymore. Now the process that we just took to do this by throwing logs into the problem that weren't there before. Whoops. Fix that. That was log y. Throwing this log here that wasn't there before is called logarithmic differentiation. Now the question is, when should we use log differentiation? This problem didn't say use log differentiation, it said take the derivative. Sometimes you'll see questions that say use log differentiation. Well, usually I'll do it when I have a fairly complicated quotient or product, okay? Because what logs do is they'll break apart quotients and products using addition and subtraction. So that's typically when I'll use log differentiation. If I have a simple quotient or a simple product, I don't bother going through this because you could actually make it more complicated. But this helps you in some ways to avoid the quotient rule, the product rule when they are fairly involved. So you throw a log into the problem on either side of the equation, use that log to expand the one side, okay? Then take the derivative of both sides, this side being y prime over y, this side using just your derivative rules. Move the y to the other side of the equation, replace with what that actual y is equal to, simplify this side, cancel when you can, get your answer. All right, last thing for us to cover here for logarithms is this derivative. Notice it doesn't look like a whole lot. In this case, it says the derivative of log of absolute value of u is u prime over u. Well, that's no different than what we've already seen. We've already seen that the derivative of log u equals u prime over u. Well, what this is saying is that if I do the absolute value of u, the derivative rule doesn't change, which is kind of unique in that that's not usually the case. Absolute values tend to make a big difference when we're doing derivatives, but in this case it doesn't. Now, why is this any significance? It'll have more significance when we talk about integration, but for differentiation, it doesn't seem to have a whole lot of difference. But think about it this way. Look at two functions, y equals log x and y equals log of absolute value of x. The y equals log x function looks like this. Okay? It goes through this point 1, 0. The domain is strictly positive values. The range is all real numbers. Okay? Has a vertical asymptote here at the y-axis. Now think about this one here. When x is positive, the absolute value of x is the same thing as x itself, right? Absolute value of x equals x if x is greater than 0. Think about if you plug 5 into the absolute value, you still get 5. So the idea is for x's that are positive, this function will look like this. Same as what we had over here. Goes through this point, 1, 0, etc. But I can now plug negative x's into here because I'm going to then take the absolute value of it and then take the logarithm, which means all these x's over here can be used. And what happens is I get this branch of the graph. And it goes through this point, negative 1, 0. And so if you think about it, this function contains this function plus has this whole other branch to it. And the domain is now all x except x equals 0. So much bigger domain than what we had here. And so this is a stronger function in many ways than this one is, in that this one contains this function plus more. And the fact that the derivative rule is exactly the same is pretty nice. And so that's going to have some consequence when we start talking about the next major topic, which would be integration. For right now, it doesn't really have a whole lot of effect. If I said, what if y equaled log of absolute value of, say, x squared, and I found y prime, it would still be 2x over x squared. I can simplify the x's and get 2 over x. You wouldn't do anything different. This is your u. You do u prime over u, and you pretty much don't really care about the absolute value that much. But again, it will have more consequence later.